Hello, class. Welcome back. 3.6 chain rule, our last generic rule. And like I said in class before this lesson, okay, this is our last big rule that we have to learn. But I'm going to go back and we're going to sit down and we're going to talk about what does it mean to write functions as composite functions, f of g of x. So I want you to do on these first examples is I want you to go ahead and break these things into two separate functions, f and g. Okay, f of x and g of x. So I wanted you to say I want f of x and g of x. I want f of x to be the overarching or my shell function. Okay, right? My shell function, just like that's a shell of my M&M. Okay. So in this one, my shell function, the one on the outside is sine x. The one on the inside, my chocolate function, is going to be 7x. What I want you to do is I want you to pause my video, and I want you, actually I'm going to pause the video for you, and we're going to go ahead and I'm going to have you do the rest of these and see if you get the same thing. Remember, f of x is your shell function, g of x is your chocolate function. Alright, here we go. And bam, there they are. Take a moment, check them out, okay? The only one I would say that you might have been balking on is e. Okay, e is technically a constant times a function, but I was kind of stretching on e there, so it can be 7x times tangent x. Okay, 7x and then g of x, your inside function is tangent x. It'll work out the same. Okay, so here we go. Let's go ahead and do the next one. Let's see here. Oh. It says here, find the derivative of the composite function y equals 2 times 3x minus 5. So then they say they're going to describe it here. Let u equal 3x minus 5 and rewrite the given function as y in terms of u. Okay, so here's what I'm going to do. I'm going to do what it says. Now this is a little bit different than what we did in class, okay, with M&Ms, but I want you to follow me through here on this, all right? So if I let u be 3x minus 5, or my chocolate function, right, I can rewrite y in terms of u as being 2u. Okay. Now let's go ahead and find the derivative of this composite function. All right, so what if I were to find the derivative of y equals 2u first? Okay, well, I'm taking the derivative of y, right? I'm going to take the derivative of y. Now, what am I taking it with respect to? U. I'm going to take it with respect to u. And when I do that, I'm going to sit down there and it's going to become just 2, right? Because 2u to the 1 is just going to be 2. Now let's come over here and take a look at u. U is equal to 3x minus 5. Well, what happens if I take the derivative of u? What am I going to take it with respect to? With respect to x, dx. Say that that is equal to 3. Huh. That's interesting. I get a 2, I get a 3. Well, what derivative am I supposed to do with it? Well, let's pause for a second and find out. I'm going to pause for a second. Let's go grab a different color. Why? I like colors. What if I were just to take my function up here, y is equal to 2 times 3x minus 5, and I go ahead and I'm going to expand this out. And I expand this out to be y is equal to 6x minus 10. So now when I go ahead and take the derivative of this, I get y prime is just equal to 6. Huh, but remember, what is y prime? Y prime, I took the derivative of y with respect to x is equal to 6. Huh. I have the number 2 and the number 3. How could I possibly get the number 6 from those two? Oh, I bet I can multiply them. If I take 3 times 2, I'm going to get 6. So let's write this out here. I have the derivative of u time with respect to x times the derivative of y with respect to u, which is equal to 3 times 2, which is equal to 6. Aha. Okay, great. So you might have remembered when I told you way back when I said, hey, you know that whole du dx, remember, never, ever, ever means divide. Unless it's convenient. Do you see why it might be convenient now? Because if I multiply these things, and I look at this, and I'm looking at this, I'm thinking, oh, wouldn't that be tempting? Wouldn't that be tempting? So now it's kind of convenient that they can kind of be represented that way as being a dividing. So I can kind of see that that's being dy dx is really equal to 6. Ooh. I wonder if that can be applied in other places. Okay. So that's where it comes up. That's why mathematically it works. Okay, what we were talking about earlier today. Let's go ahead and keep going. Next. Woo! Big giant function. So we're going to do this both ways. Okay. We're going to do this with the peanut in the shell way. Okay. And that's what we're going to do here. And we'll do that in green. And then here it is. It's all expanded out already for us. So we're going to multiply it out. Okay. And we're going to see what it looks like. Okay. And we're going to do it both ways. So first way, chain rule. Chain. So here we go. What you can identify, you can kind of see is that, actually I can do it in red. We're going to do here is 3x squared. All right, that's my chocolate function. And I have this big giant blob, if you want to, cover it up, kind of cover it up. Okay, cover it up, boom, cover it up, and pretend it's like a big giant X. All right, so that's my shell, right? There's my shell. Something squared. So when I go ahead and take my derivative of this something squared, my shell, right? Taking a derivative of my shell. Okay, derivative of my shell is going to be y prime. Okay, so this is a big X squared. So 2, leave the X alone. We'll find out and to the first power. Okay, but what was that again? Well, that again was this over here is 3x squared plus 1. Okay, so I'm going to rewrite that back in there. 3x squared plus 1. But I'm not quite done. Times the derivative of the chocolate, 6x. Oh, okay. Well, then I can go ahead and multiply all this out. Okay, that's going to be 6x squared plus a 2. Okay, times a 6x. Multiply that out, that's going to be a 36x cubed plus a 12x. And that's what my y prime is going to be. Let's see what happens when I do it the old-fashioned way. When I do it the old-fashioned way, y prime is now going to equal 9 times 4, well, that's 36x to the third power plus 12x. And you're going to be like, wow. Now here's the deal. You're going to say, well, wait. Why do I have to do it the first way with chain rule when this way is so much easier? You gotta realize this is an example, right? This is not going to be the norm all the way. Okay? This is not going to be the norm. You need to, so this is not going to be the easiest one. This is just to get you into it. All right? So let's take a look at some more. Okay? So here's my general rule for chain rule. All right? If I want to take the derivative with respect to x of a combination, okay, of functions, it's the same thing as saying take the derivative of the shell, but leave the chocolate, times the derivative of the chocolate. Okay? Or if y is in terms of a function in terms of u, like the one example I just did, the first example, and u is equal to g of x, then I'm going to go ahead and I'm going to take the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. Okay? That's a formal. We're okay with that, right? So let's take a look at these. So here we have a whole bunch of examples. Okay? I'm going to do a couple. So here we go, and I'm going to let you do a couple. Okay? These are examples from the beginning. All right? So here we go. I'm going to go get my... I'm going to create some little blocks here. This is my inner function, right? My outer function, my shell function is sine of x. There's my inner function, 7x. So I'm going to go ahead and say, well, I want to take the derivative, y prime. Y prime is equal to, well, what's the derivative of sine? Cosine. What's the derivative of, okay, cosine of blah, wait, my square. Well, what's my square? Let's go and uncover that again. Oh, yeah, that's right. That's 7x times, now I got to take the derivative of my chocolate. Derivative of my chocolate is 7. And I go ahead and simplify. 7 cosine of 7x. Okay. So now let me go ahead and take a look at this. This one here. Well, before I start dealing with this one, I want to rewrite it because I always like to rewrite my square roots. I was going to rewrite my square root as 3x plus 1 to the 1/2 power. And now hopefully what you can see is that the 3x plus 1 is my chocolate function. So now what I'm going to do is I cover that up, cover this up, okay, and then now I do my power rule. I take the derivative is equal to 1/2, leave the chocolate alone, plus 1 to the, reduce my power, negative 1/2, times, okay, derivative of the derivative of my chocolate, 3. Okay, the negative exponent means I have a denominator that goes in the denominator. The 2 is in my denominator. The 3 is in my numerator. So when I rewrite this, this is going to be equal to 1 over, or 1 times 3, all over 3x plus 1 to the 1/2. I want you to take some time and do these next 4 and see if you get the same answers that I do. All right, so I'm going to pause the video. Here we go. And bam, there they are, all those wonderful derivatives. Okay, so take a look at them, check them to see if they work for you. Okay, especially F. There's a lot going on here in F. So take a look at that. If it works for you, great. If it doesn't work for you, come with those questions. All right, here comes your assignment. Bada bing. Okay, notice here it says omit number 11. That means don't do it. Okay, and 17 to 15.5 odd. There are a lot of problems. If you have any questions, feel free to holler.